ever just stopped and wondered, what makes the universe tick? Why do things happen the way they do? Well, it turns out there's this fundamental set of rules that governs pretty much everything, from stars exploding to the ice melting in your drink. These are the laws of thermodynamics, and today we're going to dive right in and figure them out together.
Okay, let's start with something super simple. Picture this. You've got a hot cup of coffee on your desk. It will always, and I mean always, cool down to match the room temperature. But have you ever seen a lukewarm cup of coffee just spontaneously start boiling all by itself? No way, right? That's simple, everyday observation. That's our first big clue to a massive cosmic mystery.
The science that explains this whole thing is called thermodynamics. It's basically the study of how energy, heat, and all the stuff in the universe interact. Think of it as the official rulebook for how energy behaves, and it's exactly what we need to answer that question about our coffee cup.
All right, so what is this driving force that makes our coffee cool down? What makes some things happen all by themselves, while other things, well, they need a little push? Scientists have a special name for this. They call it a spontaneous process. Now, don't get hung up on the word spontaneous. It doesn't mean it happens in a flash. It just means it's going to happen naturally, on its own, without you having to do anything. A hot drink cooling down? Spontaneous. A rock rolling down a hill? Spontaneous. The universe clearly has a preference for certain things to happen, and we're about to figure out exactly what that preference is.
Our first suspect in this investigation comes from probably the most famous law in all of thermodynamics, and it's all about being a good accountant for energy.
You've probably heard this one before. The first law of thermodynamics is a pretty straightforward but incredibly powerful accounting rule. It just says that the total amount of energy in a closed system, like, say, the entire universe, is always constant. You can move it around, you can change its form from heat to motion, but you can't create it from nothing, and you can't make it disappear. It's why you can't build a perpetual motion machine. You just can't get more energy out than you put in. We could even write this down as an equation. Now, don't let the letters scare you. All this is saying is that the change in the system's internal energy, that's delta U, is just the heat you add, which is Q, plus the work you do, which is W. Think of it like balancing a checkbook for energy. But to do that right, we have to be super careful about which direction the energy is flowing. So here's how we keep score. If heat flows into a system, we call that a positive change. If the system does work on its surroundings, like a gas expanding and pushing a piston, we call that a negative change for the system's energy. These little plus and minus signs are absolutely crucial because they tell us exactly where the energy is going. Following this logic, it seems pretty intuitive, right? Maybe the big driving force is just that everything wants to lose energy. Things roll downhill, not up. They want to get to a lower energy state. In chemistry, we have a name for this change in heat, enthalpy, or delta H. For a long time, everyone thought, that's it. If a reaction gives off heat, it's spontaneous. Case closed, right?
Well, this is where our simple story gets a major plot twist. Because if losing energy was the only thing that mattered, then a bunch of things we see happen every single day, well, they just shouldn't be possible. Let's look at two types of reactions. On one hand, you have exothermic reactions. These are the ones that fit our theory perfectly. They release heat, get warmer, their delta H is negative, they're losing energy. Great. But then you have endothermic reactions. These guys actually absorb heat from their surroundings, making things feel cold. Their delta H is positive, they're gaining energy.
And this is the million-dollar question. Why does an instant ice pack get cold all by itself? That's a spontaneous process that's absorbing heat. Why does a puddle of water evaporate? That process needs energy to happen. If everything in the universe is just trying to get to a lower energy state, these things shouldn't happen on their own. Clearly, enthalpy isn't the whole story. There's got to be something else going on.
And that brings us to the second and, honestly, the more profound and mind-bending law of thermodynamics. This law doesn't just count the energy, it gives it a direction. It explains the why. The second law brings a brand new player into the game, a concept called entropy. And what it says is that the total entropy, or the total disorder of the entire universe, is always increasing. This is the arrow of time. This is why you can't unscramble an egg. It's why your coffee gets cold. The universe is on a one-way street toward a state of greater and greater randomness. So what exactly is entropy? Just think of it as a measure of chaos. A perfectly stacked deck of cards has low entropy. Shuffle it, and it has high entropy.
A tidy bedroom has low entropy. A messy one has high entropy. Well, it turns out the universe just loves a messy room. This powerful drive towards more disorder is the second major force that decides whether something is going to happen.
Okay, so now we have two huge competing forces. On one side, we have the drive to lose energy, that's enthalpy. On the other side, we have the drive to increase disorder, that's entropy. So how does the universe decide which one wins? Well, it all comes down to one brilliant master equation.
This is it, the cosmic tug of war. On one end of the rope, you have the drive for lower heat, delta H. On the other end, you have the drive for more disorder, delta S, which actually gets a bigger boost at higher temperatures. And the final result of this tug of war is called Gibbs free energy, or delta G. This one value perfectly balances the universe's need for low energy against its unstoppable desire for high chaos. And here is the single most important rule to take away from all of this. A process will happen spontaneously. It will happen all by itself, only when that final change in Gibbs free energy, delta G, is negative. That's it. That is the ultimate test. It doesn't matter if it gets hot or cold, as long as the final delta G is negative, the universe gives it a green light.
This simple table just lays it all out for us. If delta G is negative, go for it. The process is spontaneous. If delta G is positive, nope, it's non-spontaneous. You'd have to put energy in to make it happen. And if delta G is exactly zero, well, the system is perfectly balanced, it's at equilibrium, and it has no desire to change at all. And so there we have it. We've arrived at this one single, elegant equation that combines the two most powerful driving forces in the entire universe. It literally tells us the fate of almost any chemical or physical process you can imagine. You know, processes can take all sorts of different paths. Some happen at a constant temperature, others at a constant pressure. But it doesn't matter what path they take. At the end of the day, they are all bound by these same fundamental laws. That cosmic competition between lowering energy and increasing disorder is always the deciding factor.
And that's really the ultimate takeaway here. From a simple cup of coffee cooling down to the incredibly complex reactions that power life itself, everything, and I mean everything, is just a negotiation between energy and chaos. So the next time you see something happen all on its own, ask yourself, is that being driven by the need for less energy or the need for more chaos? Chances are it's a little bit of both.